This morning we're going to briefly consider the efficiency for a Carnot cycle. So let's draw a Carnot cycle. And of course in this case we're interested in the efficiency. The Carnot cycle in the PV plane, we're used to seeing this, aren't we? If we wanted to draw it, it's going to have two isotherms and two adiabats. The adiabats are, of course, insulation lines. The isotherms are where we have heat transfer. So as I go from 1 to 2, if I'm running this in a clockwise direction as a Carnot engine, this is where I get heat transfer in. There's no heat transfer from 2 to 3. From 3 to 4, I'm going to have heat transfer out, as we've seen in the past. And then lastly, I have the area inside is just the work of the cycle. We can draw this now finally actually in a little bit more of a general plane. And that's what's going to make this efficiency easy to compute. The more general plane for this problem, and we're going to find it's very useful in a number of contexts, is the TS plane. So in the TS plane, what does this look like? Well, we have basically two temperatures that we're going to be dealing with. We're going to have a high temperature, TH, and we're going to have a low temperature, TL. Right? This is my lower isotherm right here. This is TL, just like this is TH. So I'm going to have these two guys, and in order to really complete this picture, I have to have some understanding of how temperature and entropy are connected. And the way that we do that is looking at the governing equations, right? So let's write down some governing equations for this problem. And although this is written right here, this is drawn for a calorically perfect ideal gas, what we're going to find here in this plane is a much more general expression. So our governing equations, we know, let's write them down. We know that the heat transfer in the cycle is equal to the work of the cycle. That's the first law for cycles. We know that U beta minus U alpha equals Q alpha to beta minus W alpha to beta. That's the first law for processes. And rather than write down an equation of state right now, I'm going to write down the second law. So we have a couple of things we can also write down for the second law, right? We know that the cyclic amount of heat over the temperature is equal to 0. That's the second law for cycles if the cycle is reversible, right? If it's not reversible, then this becomes a greater than or equal to sign, and this becomes Ts, the temperature of the surroundings. Okay? But in the case of a Carnot cycle, as we discussed in class, it's a reversible cycle. So this is our second law for cycles, but we can also write down the second law for processes, and that looks like S beta minus S alpha equals the integral of dq over t from alpha to beta. Once again, this equal sign is for reversible processes, and each of the processes in this cycle here are reversible. They're known to be reversible because we've drawn them in this plane as continuous lines instead of dotted lines. So let's go ahead and use all of these guys in this problem, and we're going to actually find that perhaps this guy is going to be really important for us. It might be helpful at this point to just write down very briefly as well that the differential form of this looks like that, of course, right? The differential amount of heat over the temperature is equal to a differential change in entropy. Or we could write this down as dq equals TdS. And this is what we saw in class when we said that if we integrate in the TS plane under a reversible curve, we get the heat transfer in that process. So let's take a look at what we can expect here. TH, so I know I'm going to be going between two states, 1 and 2 on TH. So I should expect this to be a horizontal line, but I want to know whether I'm going that way or this way. And the way that I can figure that out is that Q1 to 2 is positive. It's heat transfer into the cycle. if I'm going around the cycle in a clockwise direction. So to have positive heat transfer, for dq to be positive, for q1 to 2 to be positive, that would mean that TdS would be positive. Well, the temperature is always positive in Kelvin, and that would mean that ds must be positive. So S must be getting bigger. So in that case, I know that as I go from 1 to 2, S has gotten larger. Well, what about from 2 to 3? Well, on 2 to 3, I have no heat transfer. dq is 0, so that means that S must be a constant. So as I go from 2 to 3, and as S is a constant, that's vertical lines, but I'm going to be going from a high temperature to a low temperature, so I'm going to be going down like this. And then the reasoning is exactly reversed for the other isotherm. Here, the heat transfer is out if I'm clockwise. It means negative. For dq to be negative, ds must be negative since temperature is always positive. So I got to go back in the negative s direction. ds is negative until I hit 4, at which case I'm going to go from 4 to 1 again on a line of constant entropy. So I get a square in the TS space. And for the same reason that I'm able to integrate under these guys and get the works, here I can integrate under each one of these curves and get the heat transfer. So Q1 to 2 is just T from 1 to 2 times ds from 1 to 2. Let's write that down, in fact. So I know to examine the inside of this guy. I know from 1 to 2, that's integral from 1 to 2 of dq. That's the integral from 1 to 2 of t ds. Well, this is an easy integral here because from 1 to 2, t is a constant. It's equal to th. So what that means is that from 1 to 2, I can write down the heat transfer as simply th times S2 minus S1. That's very nice. Okay. And then let's look from 2 to 3, right? Q2 to 3 is going to be equal to the integral from 2 to 3 of TdS. Oh, but of course, ds is 0 from 2 to 3. So I have no heat transfer from 2 to 3. And the same applies from 4 to 1. The same reasoning applies from 4 to 1. So that's my first and only heat transfer that's in existence right now. What about the last heat transfer to consider? I also have that Q4 to 1 is going to be the integral from 4 to 1 of dq is the integral from 4 to 1 of TdS. Well, now I'm sorry, from 3 to 4. This should be from 3 to 4. Made a little mistake here. 3 to 4. I already talked about 4 to 1. 3 to 4. So from 3 to 4, T is also a constant. It's TL. So this becomes very simple. Q3 to 4 here is going to be TL times integral of ds is S. So this is going to be S4 minus S3. Okay, so I have two non-zero numbers here. We know that this guy, S2, is bigger than S1, looking at this picture, right? S2 is bigger than S1, and so this is going to be positive. And here, S4 is less than S3, so this is going to be negative. That's excellent. We have one more equation that we can really write down in here, and that is that we've discovered that really S2 and S3 are the same number. And S4 and S1 are the same number. Okay, so what we've done so far is we've translated this kind of information that was specific for a calorically perfect ideal gas, right? This was kind of our starting picture for looking at Carnot cycles. And we've translated this to a much more general picture. Why? This picture will be very, very accurate even if it's not a calorically perfect ideal gas. Why? What do we have constituting Carnot cycles? We have two isotherms from 1 to 2 and from 3 to 4. That always looks like this in the TS plane. And then I also have 2 adiabats. That always looks like this. Why? Because what is an adiabat? It's a line of no heat transfer. When there's no heat transfer, ds has to be 0. S has to be a constant. So this is a general picture. This is in general. So this is really the picture to work with if we have to talk about general Carnot cycles. And let's lastly now talk about efficiency. What is efficiency? So efficiency, we said broadly, is what we want over what we pay for. Right? We need to kind of know that in a general sense, we'll refine it as we go on in the rest of this course, that what we want over what we pay for defines how efficient my process is in a general sense. Well, what do I want in this problem is the work of the cycle. Okay, and what I have to pay for is the heat that I put into the cycle, Q1 to 2. All right. I know that the work of the cycle is equal to the heat of the cycle. I know that from looking at the first law for cycles. In this process, there's only 2 processes that give me heat transfer. It's Q1 to 2 and Q3 to 4. So, and we've just figured out what Q1 to 2 is and what Q3 to 4 is. Let's plug this guy into our equation for efficiency real quick. So efficiency now is going to be Q1 to 2 plus Q3 to 4 over Q1 to 2. Well, Q1 to 2 over Q1 to 2 is 1. Plus Q3 to 4 over Q1 to 2. That's not too difficult. Let's plug in what 3 to 4 and 1 to 2 are. So this would be 1 plus Q3 to 4. That's going to be TL over S4 minus S3 divided by Q1 to 2 here. Q1 to 2 is TH over S2 minus S1. And that's great. And then lastly, let's use our adiabatic constraint here. So really, S4, for instance, is S1. And S3 is S2. So in the numerator here, I have S1 minus S2. And the denominator, I have S2 minus S1. Well, this becomes -1. So eta now is just shown to be 1 minus TL over TH. And this is the Carnot cycle efficiency regardless of the equation of state. So this is the general result. And what it basically says is that I can find the efficiency of any Carnot cycle given the low and high temperatures. And also, if I'm given the efficiency in one of the temperatures in the cycle, I can get the other temperature in that cycle. This is a really excellent first kind of look at efficiency, and we will develop it in the rest of the course.